Welcome all. So I believe, so do one thing, please mark your attendance in the comment section so that I get to know who all are there. So we will be waiting for a couple of minutes for others also to join in, and then we'll start. Okay, so let us start the session. Before we start, we just need to jot down what all topics are there in the upcoming PT. So we will first, try and see what we have already covered, and then we will try and revise as much as possible. So gravitation is a chapter which was, which has been done of late. So I will start from there, and we'll see if time permits. We'll go back and revise Newton's laws and motion chapter. Or if you want any other topic to be discussed before, you please mention either in the comment section or in the group, wherever possible. So I believe these are the topics for the upcoming PT. I'll just write them down here. So first is motion. Then we had Newton's laws of motion. Newton's laws of motion. And third is gravitation. And in some schools, pressure is also included. Okay, so today's session will be dedicated mostly towards gravitation, and if time permits, we'll take up other topics as well. Okay, so let's take up gravitation. Yeah, so I believe we have already discussed in KRM once, and for HSR people, we will do it afresh so that it becomes a revision for KRM. And yeah. Okay, so where do we start? So that our moon goes around Earth. These are the very common examples given to explain gravitation. So this is where Newton's so gravitation was one of the concepts which actually ignited Newton's imagination, and he ended up giving, let's say, the Newton's laws of motion. He also came up with calculus and various mathematical tools attached to that. So you can say that gravitation, the concept of gravitation, led to a lot of scientific discoveries and development of lots of laws and Theory. So basically, a little bit of history about how science evolved, and we have discussed that early Greeks used to do something called astronomy. So so astronomy was a science that time, and out of the four subjects in quadrivium, which we normally know, quadrivium were the four subjects which the Greeks used to study. And it included what all? It included music, which was studied along with arithmetic, and then there was astronomy, and then there was something called geometry. So these were the so there was no physics, chemistry, mathematics, and biology that time. People used to study subjects like that. Okay, now it all started with let's say astronomy. So astronomy was developed, and people started tracking the stars and tracing them, and trying to kind of explore more about them, and they started finding trend in their motion. Now, so this particular science was practiced by lot many people, and then as you know that there were people like Tycho Brahe. Then there was a guy called Johannes Kepler. Whose three laws of Kepler's laws were very famous. Johannes Kepler, whose work he gave three laws in planetary motion, and these laws were later utilized by Newton to propound his own theory of gravitation. So this is how it went, right? Then there was a guy called Copernicus. So you know the story of Copernicus. He was executed because he challenged the church, saying that Earth is not the center of the universe, but actually it goes around the sun, and Earth is not flat, and things like that. So he was executed because he went against the dictum of the church. So these were the pioneers of this, and then came the very famous Galileo. Who did pioneering work. He is credited with the invention of a tool called telescope, which facilitated evidences, right? So now he can come up with lots of evidences about all these theories. And then later on, you know that 1642 was the year when Galileo died, and then Newton took birth the same year, and rest is history. You know how today we follow the laws of gravitation and what goes behind it. And today is the cutting edge research in physics is going on in this field. And just to give you a reference, that there is something called LIGO experiment going on, where the study on gravitational waves are going on. Gravitational waves. So this is a very important concept in physics. In fact, lots of research work is going on in this area, gravitation. Now, just a moment, guys. So now, what in your so this was a brief introduction about gravitation and the people attached to it, but then the subject matter remains this, that we will be studying first. So I'll just give you a brief of, first of all, Kepler's law, because these were the reasons why, or let's say the basis of Newton's law of gravitation. Then we'll also study about Newton's law of gravitation. Okay. Then we will try and find out, understand what is acceleration due to gravity. Acceleration due to gravity. And then we'll try and find out, or let's say we'll do, numerical problems on, let's say, motion of objects, motion of objects under the influence of gravity, right? And then we'll also understand the concept of mass versus weight. What is the difference between these two concepts? These are the main topics under the chapter gravity. Okay, so let us start with Kepler's law. So Kepler's law. So we are going to do Kepler's law. Kepler gave 3 laws of planetary motion, and the first law was uh, law number 1 was it's called law of orbit, and he said that planets go around the sun in elliptical orbits. This was his first law. What does it mean? So basically he said that, okay, so unlike the popular belief during that time that Earth was the center of the solar system, and it appeared to be so. Why? Because people used to see sun setting down and rising up every day, and they believe that there's only one possibility why it is happening is all the celestial objects are moving around the Earth, which now as a student of physics, you have already done motion. You know how motion is relative, so hence something which appears to be moving with respect to you, could be the other way around, that is you are moving with respect to the body which you think is moving. So the same logic applies here. So hence Kepler said that, okay, there is a planet, let's say there's a star, like our sun, star sun, and then this is the sun, and planets have an elliptical orbit like that. Yeah, so it's not circular, so they do not go into circular orbit. So I'm not able to draw it very, let me try and show you how ellipse looks like. So this is how it will look like. Yeah, so this is how, and then there will be a planet just in the, yeah, so it will not be the center. So they say, and he said that the planets go around the sun elliptical orbits. So let me just take this away. Yeah, so this is not required. So what did he say? That, okay, so there is a planet, there is a sun, there is a star at one of the focus. So but what did he say? He said that planets go around the sun in elliptic orbits with the sun located at one of the two foci. Okay, now in an ellipse, if you see an ellipse, how does an ellipse look like? I'll tell you. So let's say again, I will draw ellipse to explain. Let's say this is an ellipse. So there is something called the axis of the ellipse. So let's say this is called the minor. So let me explain the concept of ellipse to you. So this is an ellipse, and this was the minor axis, and then let's say this is my major axis. Sorry, this is the axis which has been highlighted is the major axis, and let's say this is called the minor axis. Yeah, minor axis. Right now, on the major axis lies a point. There are two points which lie on the major axis. So what am I saying? This is major axis, and this one is minor axis. Okay, so this length is A, and this length is B, which is called semi-minor and semi-major axis. Now these 2 points, this is called, let's say, S1 and S2. So S1, S2 are the focus of the ellipse. And what does focus mean? We had explained that, if you take any random point on the ellipse, let's say this one, and try to join this point with both the foci. Now the sum of the distances between this, let's say, point A, so AS1 plus AS2, these two distance is always a constant. Whatever is the value, but it will always be a constant. Meaning what? Whether A is here or here or here or here, whenever you will find out the sum of the distances of this point with the two focus, you will get a constant distance. That's the significance of the focus. Now, so here, what did Kepler say? So Kepler said that, okay, sun would be on located at one of the foci, okay, and the planet would be going around the elliptical orbit. This is how he explained. This is what he meant. This is his law number one. Then he came up with law number 2, and he said that, and this was law of area. Law of area. Now, what is that law of area? What is that law of area? The law of area said that the area swept by the line, joining the planet and the sun sweeps equal areas in equal interval of time. What do I mean? It means this, that if you join these two lines or these 2 points, let's say the sun and the planet. Okay. Now let's say after some point the planet is here. Right? Join these 2 points also. Okay. Now the area covered by the planet in this time. Let's say this particular time taken was t, and the planet moved from point number A to point number B. On the other side, let's say planet was somewhere here in C, and then it moved into D. Okay, so somewhere here and somewhere here, D. Okay, and this time taken also was, let's say, T. So the area swept in this time interval. So let's say area of triangle, or it's not a triangle, so to say, because it's a curved side here, but for understanding, let's say that, okay, area of this shaded area, this region is same as this region, right? This is what the law of area says. So area swept by the line joining the planet, let's say this is S sun. So SA, this line joining the planet and the sun in a given interval of time is same always. Yeah, this is the law of area. Third law was law of time period. Third law was law of time period. What is time period? Time period is defined as, so let me define time period. Time period is defined as time taken by the planet to complete one revolution. Okay, so in case of Earth, you know that in 365 and quarter of a day, Earth completes one rotation around the sun. So that's the time period for Earth. Okay, so law of time period says that law of time period says that cube of semi-major axis. Semi-major axis. Or we also say that average distance between the sun and the planet. Okay, so what is it? Law of time period says that the cube of semi-major axis, or so this is, you can either you take that, or average distance between the sun and the planet. I'll explain what does it mean. Is directly proportional to the square of time period, which is written as r cube is directly proportional to t square, right? So t, you understand. So t is the time period, that is the amount of time taken by this planet to go around this. So let me just copy this diagram so that I can explain it there. So let us say it is here now. So if you see, what is r? R, you can either you can take r as, what you can do is, r could be this. This is the semi-major axis. So if you draw the ellipse, so this point from this is called center of the ellipse to this point. This is called the semi-major axis. Why? Because the full side was called the major axis. This a half, if you remember, see, I drew it here. So this a is called the semi-major axis. Now semi-major axis. Okay, law of area. I'll repeat once more, Nihal. So Nihal is asking what is law of area, but let me complete this law of time period and then I'll go to law of area. So so this a is the semi-major axis. So hence we say that, or let's say if we call it as r, so r cube is directly proportional to t square. This is the Kepler's third law, and what is meant by this particular phrase, average distance between the sun and the planet. See, if you see, the planet is at different distances from the sun. Now what you can do is, if you find out the average distance means add all these distances and then do what? Divide by the number of time you calculate this, you will get the average distance. Yeah. So this or either you say this, or say this, that semi-major axis cube is directly proportional to time period square. Now going back to what Nihar is asking about, what is law of area? Law of area says that the area swept by this line. So for example, initially the planet was here at point A and it went to point B. Now let's say it took time t for the planet A to go to B. So the area swept by line SA is nothing but whatever has been, in the shaded form. This area was swept by line SA in time t. Okay. Now let's say the planet was at C at any given time, and after it took another, let's say in a time interval of t, which was same as this time interval, the point C or the planet C has reached point D. So if you see this area again, area swept by this line CS, area swept by this line in time interval t. So this is the area swept by line, this much. This shaded area is the area swept by line. So this area comes out to be same as this area. Okay, so let's say in 1 second or in 1 day, Earth goes from A to B, and in let's say in another day, Earth goes from C to D. So the area bounded by these lines, so the line joining SC, SD, and this curve CD is equal to line joining SA, SB, and the curve AB. This is what law of area says. Okay, now coming back to the law of time period, and this was where Newton picked it from here, and he gave his law of gravitation. So what is it about? Before that, there was an assumption. An assumption is, what is the assumption in Newton's laws of gravitation? Let's say assumption is, for all practical purposes, Earth goes around the sun in almost circular orbit. So mark the word, it says almost circular. It's not circular, but for all practical purposes, you can assume that it goes in circular orbit. Now, what happens in a circular orbit? Let's say I have a circular orbit. Now, circle is different from ellipse because you can say first from the shape itself, it looks different. And there is no concept of focus here. Yeah, there is something called center of Earth. So let's say I had this center of Earth. Oh, sorry, center of the orbit around the sun. So this is sun. So let's say sun is at the center, and Earth is here, and Earth is going around the sun in this manner. Okay. Now what happens is we say that the force acting here is nothing but the force of attraction, the gravitational attraction. Newton found out this force of attraction, yeah, F gravity, because of Earth was directly proportional to the product of the two bodies. That is what the F of gravity is directly proportional to the mass of sun, let's say m1, and mass of Earth, let's say m2. Okay, so this force of attraction was directly proportional to m1 into m2, first of all. But what is m1? M1 is mass of sun, and m2 is mass of Earth. And you know the meaning of directly proportional. Directly proportional means if you increase m2, the force will go up, and if you increase m1, the force will again go up. Now this is not so. Later on, he kind of generalized this theory, and he said that it need not be only the masses of sun and Earth. Between any two objects, he said, and it will be later generalized for any pair of two objects. But right now, let us say that the force of gravity is directly proportional to m1 times m2. Also, he found out the force of gravity is inversely proportional to the square of the distance between the two. So let's say this distance, let's say at any given point, is r. Okay, let me draw a better figure. Let's say this was sun at any given instance, and this was Earth, and you join the two centers, center to center distance. So what is r? R is equal to center to center distance. Center to center distance between the two bodies, planet and the sun. Okay, so Newton found out that Fg is directly proportional to 1 by r square, or we say it is inversely proportional to r square. So these are the two things. So this particular law, or this particular relationship where the force is directly proportional to or inversely proportional to the distance. What does inversely proportional to distance mean? If you keep on increasing the distance between the two objects, let's say if r goes up, Fg goes down. What am I saying? If r goes up, Fg comes down. Yeah, and small, even either there will be, if you increase the r by a small distance, Fg goes drastically down. Okay, so if you let's say, you can take the case, for example, if let's say if you reduce or double the distance, the force of gravity becomes 1/4. How? So let's say, if this was the case, if Fg was, let's say, directly proportional to r square, if r becomes, let's say, 2r, now let's say r becomes 2r, then what will happen? It will become 2r square, which gives you 1 by 4r square. So the force will just drop by 4 times. So if you double the distance r, force drops by 4 times. If you triple the distance, you multiply it by 3 times, the force will drop by 9 times. It will become 1 by 9 r square because of this square thing here. That's called inversely proportional. And then, okay, so hence this is what Newton figured out. And then he said that, okay, and then by experiment, if you do this, if you combine these two points, I just complete that. This particular thing is called, this particular behavior, that a force comes down like that, this particular behavior is called inverse square law. Later on in electrostatics, when you'll deal in next year, in 10th standard, you'll see there will be another similar law in electrostatics where two charges are separated by distance r. If you remove, or let's say separate them out with a more distance, the force goes drastically down between them, force of attraction or repulsion, right? So this is called inverse square law. This is a very famous concept given by Newton, that if there are two bodies separated out by a distance r, their force is directly proportional to 1 upon r square, and as you increase the r, the force of attraction goes down. I hope all of you understood this, and hence if you have any query, please keep putting down in the comment section. Now, what next? So hence let me just rewrite this too, and then we'll club them together. So hence Newton said F of g, that is force of gravity, is directly proportional to m1 m2, and is also directly proportional to 1 by r square. Now, where is this force of gravity acting? So this is the thing. So let's say the sun and the earth. This is earth, this is sun. Now sun is pulling earth towards it by Fg. So the force applied by sun on earth is Fg. If you notice, the direction of the force is towards the center of the sun. Yeah, towards the center of the sun. And similarly, this is the action-reaction pair. If you remember our Newton's third law of motion, earth will attract sun with the same amount of force, but in the reverse direction. So this is Fg. So Fg is action-reaction pair between sun and earth, right? So force of gravity, sun also attracts earth and earth also attracts sun. They have the same amount of force, right? So this is what Newton observed. And then experiments were done like this. So when it was found out that Fg, when someone, when scientists started doing this experiment where they measured the force between the two objects and calculated this quantity m1 m2 upon r square, like that, right? So you take 1 kg mass, let's say you have 5 kg, you have 10 kgs, two masses are there, 5 kgs and 10 kgs, and you measure the distance. Very easy, measure the distance. And somehow, let's say there are experimental mechanisms where you can find out the force of attraction between these two objects. And let's say the force of attraction came out to be Fg, let's say 100 Newton or some x Newton. Okay. And then what you found out are, the masses, and then you calculate this quantity, m1, m2 upon r square. Calculate this quantity. Now, every time you calculated this and tried to find out this ratio, it was always coming out to be a constant. That means now if you change 5 kg to 10 kg and 10 kg to 20 kg, and let's say change r to something else, 20 meters or 30 meters or whatever, and then again find out the force of attraction between the two, and then find out this ratio. So you find out the force of attraction, you find out the masses of the two bodies and the distance between them, and do the calculation of this. You will always get a constant, which is today called universal gravitational constant G. It's called universal gravitational constant. And its value is nothing but 6.67 into 10 to the power minus 11, and the units are Newton meter square per kg square. Okay. Now Anurag asks, why did Newton take the center of the two bodies? There's another field of, or let's say field of study where Newton has actually proven that in all these cases of analysis, we are taking the body as a point object. Point object means it is considered to be a rigid object, and a rigid object means it's not, the relative coordinates or relative displacements, or let's say positions of one point with respect to the other point never changes. That's so. For example, why it is taken as rigid? Rigid means, let's say, point A and point B. If this is the distance between point A and point B, throughout the motion, this distance will stay constant, and throughout the motion, they will have a particular relationship between their velocities. So that is not going to change. Hence, they are rigid. Now, for rigid bodies, what Newton said, that it can be assumed that the entire mass is concentrated in the center of mass. Okay, and there's another body of proofs which proves that the analysis doesn't change whether you consider the body to be having dimensions, or you concentrate the entire mass in a hypothetical point which is center of mass of it, and then you do repeat this, and you repeat this analysis, you will find no difference. So hence, point is, whether you treat it as a very big geometrical or with object with dimensions, or you treat this object as a point mass and the entire mass of the body concentrated at that point, the analysis is not going to change. So hence it reduces a lot of effort in calculations and understanding of the concept. So hence, that's what is meant by, and why did he take, let's say, the center of the two objects. Inverse square law. Inverse square law, I told you that this is what inverse square law said. I'm again repeating it. So inverse square law said that the force of gravity between the two objects is directly proportional to 1 upon r square. So if you see, this is square, and this is nothing but, or you can say this is equal to 1 upon r whole square. So square of the inverse of the distance, right? So this is the inverse of the distance and the square of it, and hence it is called inverse square law. So the force of gravity is based on inverse square law. That means you keep on increasing the distance, your force of gravity will go down and down and down. And the square aggravates the matter. That means if you double the distance, force drops by 1/4. If you half the distance, force becomes double, and things like that. Yeah, so this is called inverse. So for example, if 1 by r is doubled, so when r is doubled, it will become 1 by 2r square. So which is nothing but 1 by 4r square. So hence force will drop by fourth, by a factor of 4. If r is 3, if reduced to, if r is tripled, let's say if you increase the distance between the two objects by 3 times, then the force will go down by 9 times. That's why it's called inverse square law. So I hope I made you I could explain you. And now again, rewriting the Newton's law of gravitation, he found out Fg is equal to g times m1 m2 upon r square, where g is equal to 6.67 into 10 to the power minus 11 Newton meter square per kg square. This is universal gravitation constant. M1 is the mass of object 1, mass of object number 1, or body number 1. M2 is mass of object number 2, and R is center to center distance between the two objects. Any doubt, guys, so far? Yeah. Any doubt, please, you can keep posting on the comment section. I will understand what exactly is your doubt, and I'll try to clarify that. Okay, this is Newton's law of gravitation. Now, okay. Now let us calculate. Let us calculate the acceleration due to gravity. Okay, so the small g which you have been using, value being 9.8 meter per second square, which you have been using in your calculations in let's say kinematics or the first chapter, motion chapter. We will talk about that. So hence, what did we cover so far? We covered Kepler's law, we covered Newton's law of gravitation, and now we'll talk about acceleration due to gravity. So what is acceleration due to gravity? Let's understand that. So now let us say that, okay, let me first. Now the third topic is acceleration. Yeah. Now we know that in the Newton's law we studied what, that if by Newton's second law, what did it, law of motion? What did it say? It said that if there is a net external force, or on the other side, we say that rate of, this is what Newton's second law said, rate of change of linear momentum, or momentum of an object, rate of change of linear momentum of an object is directly proportional to net, again emphasis, net external or net unbalanced external force. Please be careful. So this is net external or unbalanced external force. Very important to understand. Net unbalanced or unbalanced external force acting on the object. Okay, so this was Newton's second law of motion. That means, let us now take this Earth. Let's say this is Earth. This is Earth's surface, and here is Earth body. And let's say there is an object here, kept over here. Let's say it is suspended in air, hypothetically. Now, if you hold it here, right, and now you release, what will happen? It will start moving towards the Earth or the surface, And if you see, there is a force which is being applied by the Earth on this body. Let me draw it different. Yeah. So what is it? So there is a force. This force. Let's say this force. Who is applying this force onto the body, and because of which it is moving? It's Earth, right? So hence, let's say this force is, or instead of writing the full this thing, I'll write. Yeah. So let's say this force, Fe. Fe is the force. Let's say, let me write here. So Fe is equal to force applied by Earth on the object. Okay, this is the force. Now, now let's write Newton's second law. Let's try and understand with the perspective of Newton's second law. What did Newton's second law say? Rate of change of linear momentum of an object is directly proportional to the net external force acting on the object. Now, the corollary to this, or when we simplified this for a case where mass was constant, where mass was not changing, then We figured out what? Force was equal to nothing but mass of the object and acceleration of the object. Yes, force acting on the object was nothing but, so again, force acting, so this is force, net external force acting on the object, on the object, on the object is equal to mass of object and acceleration of object. Right? So who's creating this acceleration? The force, net external force acting on the body is creating the acceleration. Okay, so the net external force acting on the body is creating the acceleration. So hence, in this case, this is Fe. Yeah, Fe is, so we can write from here that Fe is equal to mass of the object. Let's say the mass of object is m, and mass of Earth be, let's say, me. Okay, so force acting on the object is Fe. Yeah, and this is equal to mass of the object and acceleration of the object. Let's say the body is accelerating down, it's going down with acceleration a, which we call as acceleration due to gravity, g. Right? So I can write what? I can write F E equals m into g. Yeah, it's a is g. G is what? G is what? Acceleration due to gravity. Now this is from Newton's second law, isn't it? Newton's second law says the force acting on an object, net force acting on an object is nothing but mass times its acceleration when the mass is not changing. Okay. Now so this was for Newton's second law. Let's analyze from Newton's law of gravitation. Law of gravitation. What does this law say? He says that, okay, let's say this was Earth, and now I am drawing a smaller view of the thing. So let's say this was Earth, and this was the object. Let's say this was the object, point mass. Okay, now let's say this is the object. So if you let's say this object is at a height h from the Earth's surface, and let's say this is or r. Let me just rewrite this here from here. Okay. So what I'm saying is, let's say this is the center. So this thing is nothing but the radius of the Earth r. Radius of the Earth r. This is Earth. Okay. Now, what is mass of Earth? me. And what is mass of this object? m. So by Newton's law of gravitation, what was Newton's law of gravitation? Let's see. This was Newton's law of gravitation. Newton said the law, and let me just copy it from here and take it there. So let us say by Newton's law of gravitation, Newton's law of gravitation said that this Fg is nothing but mass of, or capital G times mass of the first object. Let's say mass of first object is me, Earth. Second object here is the small m, divided by what? The center to center distance between them. So here, this is the total r. If you see, this is r. So r is nothing but h plus capital R squared by Newton's law of gravitation. That means what? Earth is pulling this object downwards with force Fg, and it is, the object is also pulling the Earth up with Fg. But for the analysis of this object, I don't need to care about that force. I need to care about only that force which is acting on this body. So what is the force acting on this body is because of the Earth, and which is nothing but by Newton's law of gravitation, this much. Now, don't you think Fg and Fe are same? So this particular analysis came from Newton's second law of motion, and this thing is coming from Newton's second law of gravitation. So what do I mean? I can equate these 1 and 2. Both are same forces. Same forces. So from 1 and 2. So from 1 and 2, I can say Force of gravity is nothing but the same force which is acting on the body. So hence, what is force of gravity? Force of gravity is GMEM upon H plus R square is equal to mg from 1 and 2. So hence I can strike this m off. They are same. So what do I get? The value of g. The value of g is nothing but capital G times mass of Earth divided by h plus capital R whole square. Now if you see, now let's talk about numbers. So if you see, what is g? G is equal to 6.67, we just learned, into 10 to the power minus 11 Newton meter square per kg square. This was the value of G. And what is mass of Earth? If you see, mass of Earth has been calculated as 6 into 10 to the power 24 kgs. Okay, this much. And we know radius of Earth. Radius of Earth is 6,400 kilometers. Radius of Earth is 6400 kilometer, which is 6.4 into 10 to the power 3 kilometer. Now 1 kilometer is 1000 meters, so I can say 6.4 into 10 to the power 3 into 10 to the power 3 meters, which is nothing but 6.4 into 10 to the power 6 meters. This is the radius of the Earth. Right, so 1 in 6.4 million meters it is. Now, if you see, what is h? H will be of what order? So, if you see, h will be, let's say, how high do you expect an object to be from the Earth's surface? Let's say it will be hardly 20 meters, 30 meters, like that, somewhere around that. The value of h will be. Now, this value of h in front of the radius is nothing. It's negligible, isn't it? This is in terms. This is 6.4 million. And this is just 20-30 meters. So hence, for all practical purposes, we can say that h plus r is almost equal to r, because h is actually very, very small with respect to r. So hence, for all practical purposes, we can fairly assume that h plus r near the Earth's surface. So you can say this is near the Earth's surface. H will not be significantly higher near the Earth's surface. Near the Earth's surface, h will not be significantly higher. Then what does it mean? It means that you can neglect h in this particular relation, and hence you say g will be for practical purposes, for calculation purposes. I can estimate, or let's say I can do a rough estimate, and it will be nothing but g into me by r square. If you consider h to be 0. And we can fairly assume that. Why? Because h is very small with respect to r. So you will be reduced to this. And if you deploy all the values, that is 6.67 into 10 to the power minus 11 into mass of the Earth is 6 into 10 to the power 24 divided by what? R square. R square is 6 into 10 to the power, 6.4 into 10 to the power 6 to the power square, and you will find out that this value comes out to be 9.8 meter per second square. This is how, I hope you understood how the acceleration due to gravity is found out. Even if you don't you didn't understand, what you can do is, after the session, whenever you find time, this video will be available online. You can repeat the video in slow motion, pause it and understand, and if you and after that also, if you don't get it, you can always shoot a question to me. Okay, so this is how G is calculated. Now, someone may ask, what if H is significantly higher than R? Yeah, so let's say, hence, if H is, so hence now I'm saying, if H is significantly high means it's comparable to, let's say, the radius of Earth, or let's say you are talking about hundreds of kilometers, or let's say 200 kilometers above the Earth's surface. What will be the acceleration due to gravity? So if h is significantly high, you cannot ignore, we can't ignore it. So what will happen if you see? So what is the value of G? Let me again copy and write it down here. So G is this, and if you see, let me, yeah. So this is G. So if you see, if this denominator increases, which will increase as you go up and up and up, your H value, what was H? If you remember this figure, see, this was H. Now let's say you started moving up, then your H value will increase, and hence if the H value increases, denominator increases. If H increases, H plus R increases, H plus R increases, then H plus R square increases, and then something in denominator increases, that means the value decreases. So hence I'm saying if H goes up, G goes down, isn't it? So as we go up, the value of G goes down. Right. So let's say if you are finding out the acceleration due to gravity on Mount Everest, which is around 9,000 odd kilometers from Earth's surface, then your acceleration due to gravity at Everest will be marginally. It will not be a great difference, but it will be marginally lesser than 9.8 meter per second square. Always remember, the value of G is highest at the Earth's surface. As you go up, it goes down. Now someone may ask a question: what happens if you go inside the Earth? Means what? Let's say if you have Earth like that, and you dig a big pit such that you are now here at this point. Let's say this is the center of Earth. Okay, so if you go down, also G goes down. Yeah, so the value of G goes down within the Earth's surface and outside the Earth's surface as well. How it happens, for that you need to understand that as you go up, the force, let's say if you're here, the force of gravity is now applied by this portion of Earth only. Okay, so this portion of Earth, what happens? This portion of Earth is attracting the body now at this point. Let's say the body is here. So only this portion of Earth is pulling it down towards its center, isn't it? Now, obviously, as you go down, this portion of Earth will have lesser and lesser mass because now the volume has shrunk. So here, if you see, mass goes down. Mass of Earth has gone down, and something goes down in numerator. Again, G will go down. Did you understand? So hence, you learn the derivation, proper mathematical explanation to this when you learn calculus. But for the time being, you understand that as you go inside the Earth's surface, the portion of the Earth which is pulling that body towards its center, that has lesser and lesser mass, and hence effectively the G goes down as you move down or up. So if you see, this is what it is. So let's say if I plot a curve like that, what is this plot? Let's say this is center of the Earth, and this is Earth's radius. Let's say this Earth's radius R, and here is the Earth's surface. Okay, and this is as you move up from the surface. So hence, if you see, the force of gravity behaves like this. It linearly increases till you reach the surface of the Earth, and then it drops like that. It drops like that. So if you see, this is nothing but my 9.8 meter per second square. Yeah. So at the center of the Earth, there is no acceleration due to gravity. As you start moving toward the surface, the G values increases, becomes 9.8 meter per second square at the surface. So this is the surface. And then as you move away from the surface, the G value again decreases like that. No, if R goes down, so won't it remain the same? Yeah, I understand your point. R also goes down, but the significance of R going down, see, there is a there is a balancing act going on. So which one is going down more faster will determine the value of G. Very good question. Aditi is asking. I think Aditi, yes. Aditi is asking, when I say that if you go down, mass goes down, but R also goes down. Yes, definitely R goes down, but the battle is won by the decrease in mass, because the amount by which ME goes down is not compensated by the amount by which R goes down. Okay, so hence this is going down and this is going down. So who will decide whether G effective, if in the who wins in the battle? Who will make who will determine whether G will go down and not? Depends on who goes down faster. So if mass goes down faster, then it will take G value down. What do I mean? If the effect of mass going down is higher than effect of R going down, then obviously G will go down. On the contrary, if the effect of mass going down was lesser than effect of R going down, then G will go up. Hence I said, once you learn integral calculus, you will get a mathematical explanation of that even when the mass goes down, the effect of mass going down in that particular segment, for example, when it goes down here from this height to this height, the mass which goes down is much higher in effect than the simple radius going down. Why? Because if you see, mass is of the order of 6 into 10 to the power 24 kgs. But radius is of the order of 6 into 10 to the power 6 meters. Even if you square, it will be 36 into 10 to the power 12 meters. Right? So it's still, the mass has got an upper hand. So if it goes down, its impact, its impact in the same distance is higher than the radius itself. So radius is kind of playing a smaller role in bringing the G down. Is that okay? That's the explanation. But yes, this is a qualitative explanation. Once, as I told you, let's say when we cover calculus, you will get a mathematical expression also, where it will clearly show that if M goes down, G goes down. Okay, clear. Now, so this is about, what did we find out? We found out we found out the value of G, and this is how G behaves at different points of the Earth's surface, within the Earth's surface, outside the Earth's surface. Now, we'll see the fifth point. What all points did we cover so far? So we covered acceleration due to gravity also. Now let us see motion of objects under the influence of gravity. Okay, motion of objects under the influence of gravity. So again, in motion chapter, if you remember, we were talking about motion in 1D. How is there no gravity at center of Earth? Okay, so basically, Kshitij is asking, why is there no gravity at the center of the Earth? Very good. So let's see, why is there no gravity at the center of the Earth? To understand that, you need to understand, yeah, very good. Aditi gave the answer. At the center, the entire mass is outside, isn't it? All the mass which is distributed in the Earth is outside that center, isn't it? To have this, so if you are at the center, there is no mass there. So if there is no mass, how can there be any gravity? That's the, yeah. So the moment you go even an inch outside that point, you can consider that the entire point is concentrated at the center. Yeah, by Newton's let's say Newton's work, he proved that when you are let's say analyzing this body from outside, okay, then what you can do is you can treat this entire mass concentrated at the center, and then you can do the analysis. But when you are there present at the center itself, there is no mass. Yeah, so at that point there is no mass, and hence there is no force of gravity because at the center of the Earth. And when we say force, there is no force of gravity at the center of the Earth. No. So another question is, but at the center R is also equal to 0, then G must be infinite. Now, see, infinite, when we say, you are talking about 0 by 0 term. This is not infinity, my friend. So this is not infinitum. It is, in mathematical concept, it is undefined. There is no infinitum here like that. Okay, so when I say, understand this, when I'm saying that at the center there is no mass, so hence there is no force of gravity on the earth due to itself here at the center. Okay, there is gravity acting on the earth because of sun and celestial bodies, because they are outside the system of earth, but at the center there is no mass, so hence when there is nothingness, there is no question of gravity. I hope I could understand. I could make you understand. So this is the concept why the gravity force of gravity keeps on decreasing, and then eventually at the center it becomes zero. So everything is defined. Let's say force of gravity. The first thing is that there has to be mass first, because the existence of gravity depends on the first thing, and that is the mass. So hence, if there is no mass, we cannot really work on gravity. So with that logic, now going ahead. So hence, there is this Earth again, and this body is, let's say, dropped from here. So when it is dropped, it starts moving downwards. And why does it move? Because of Newton's second law. He says that if there is net external force acting on the body, it will accelerate. Yeah, so we are talking about, let's say, no, it's so the next question is, if G is undefined, we cannot assume it to be zero. No, so it's, please understand, we are using mathematics to define physics. It's not the other way around. Okay, so 0 by 0 is infinitum in what we have kind of, many a times you wrongly use also in mathematics, is not applicable here. See, the thing is, we first of all understand the natural, see, physics is what understanding the how nature works. Now in this case, we observed with experiments that mass is the first criteria to define the existence of gravity. Okay, so if there is no mass, whatever mathematics says is secondary. First of all, we cannot define the existence of force of gravity itself. Whatever mathematical interpretations are happening, that's a second thing. First of all, there is no mass, so hence there is no question of gravity in the first place. So hence we cannot, go ahead and define 0 by 0 or whatever it is. Okay, so another question which is coming out to be is, if acceleration due to gravity decreases or increases in height, then why does G go down as we go to the center of the Earth? I just explained. I explained this. As you go down, the effect of mass getting reduced is much higher than the radius getting reduced, and hence it is. Okay. Okay. Now, so the thing is, this body. Now coming back to the discussion, and the discussion is motion of objects under gravity. Motion of objects under gravity. So what is it? Basically, let's say if there is an object which is let's say you are holding it at a height. Let's say this is height h above the Earth's surface. Okay. Now this object is released. So what will happen? What is the force acting on this object? Always we say that W, weight of this object, and which is nothing but mass times its gravity. So hence work done is mass times its gravity. Sorry, not work done. I'm really sorry. So weight is mg. So mass times gravity is the force acting on this body. Okay. So hence we say that this body is undergoing an acceleration g. Okay, and this is a 1D motion, 1D, one-dimension motion. That means the motion is happening in one line. The motion is restricted to one line. Motion is restricted to one line. One line. Yeah. So hence we can apply the three equations which we studied. If you remember, the three equations of motion were: equation number 1 was V equals U plus AT. Okay. Second was S equals UT plus half a t square, and third was v square is equal to u square plus twice as, and then the other point to be taken care of was the sign convention, the signs, because all these parameters v, u, and a are vector quantities, so signs are important, sign convention. So we had a sign convention. What is that? If you have to first take what, do what, define a positive direction, define a positive direction, positive direction, yeah. All the vectors aligned to positive direction are taken as positive, otherwise negative, otherwise negative. What do I mean by that? So let's say in this case, let's say this is Earth, and you're considering this to be positive direction towards the sky is positive, let's say positive, positive. Now if the body is moving down, right? So let's say it started moving down with u. So is u same as the positive direction? No, so u will be negative. Acceleration is downwards, so hence a is also negative, yeah, right? And the displacement, so what is the displacement covered? Let's say this guy came from, yeah, from this height. So it was initially at, zero, sorry, at some height h, and it came down to 0. Okay, so whether it will be positive or negative, if the displacement was towards the sky, so that was initial displacement was this, so it was positive. So hence likewise we will treat u, and let's say at a given point the velocity is like this, at any instance velocity is like that, so it's again negative. Why? Because it is against the positive direction, right? On the contrary, if something is thrown up, so this is when the body was thrown down, let's say the body is thrown up from grounds up, and this is your positive direction, so what will happen? U is positive, and then but acceleration is still negative. Why? Because at any given point the acceleration is acting downwards, right? So a is still negative, right? And the displacement covered is positive because it is moving in the direction, positive direction. Okay, so this is, you please take care of sign convention, and there is no restriction that you should take positive in towards the sky. You can also take positive in this direction. This can be also treated as positive, no problems at all. But then accordingly, the moment you take this as positive, then u, v, a all becomes positive. So you please take care of. Isn't a equals to g? Yes, the value of acceleration is g. Value of acceleration is g. But what did we learn? The question is, if a is equal to g, how is it negative? Negative and positive is coming because acceleration is a vector quantity. And hence a negative sign to g signifies that the acceleration is in the opposite direction of whatever positive direction you have chosen. So hence negative sign is just to indicate that. You know, we know that all these u, v, a all are vector quantities. So you must take care of the signs as well, because we cannot simply treat vectors as scalar quantities. Okay, now let's take up a problem to understand so that it becomes easier. Let us take a problem. So the problem goes like this. Let me. Yeah. So the question goes like this, and I'm writing it. Question is a question. So let us solve a question. So a stone is dropped freely. Dropped freely means it was not pushed down. Dropped freely, that means initial velocity was 0. Okay, so a stone is dropped freely from the top. from the top of a tower, and it reaches the ground in 4 seconds. The ground in 4 seconds. Okay. It says taking g equals 10 meters per second square, calculate the height of the tower. This is a practical case of using g to find out height. Calculate the height of the tower. So you can do this activity in your building also, but yes, you have to have a very sophisticated stopwatch and repeat it 5-6 times, and you will get to find out the height of the building. So as I have always told you, it's very good method, or let's say very good practice of first of all trying to capture the question in a form of an image. So let's say this is a tower. This is a tower, and from here, let's say there's a platform, and the object is dropped. Freely dropped means initial velocity u is equal to 0. Okay, let us say the height of the tower is h. Okay, height of the tower is h, and what is to be found out? It takes t equals to 4 seconds to come down. So when it's here, when the object comes down here, it takes 4 seconds, and you have to find out h. H is equal to what? Okay, so, and again, as I told you, if you are not very clear on what formula or which particular equation to be used, then best practice is to write in some part of the sheet all the three together. So let me write again for your convenience here. V equals u plus at, s is equal to u plus ut plus half at squared, and v square equals u square plus 2as. These are the three equations. You have to just take care of a and g and the direction. So I will take, let's say it's my choice, so I will take this side as positive. So the moment I say this, then I get what? Let's say h. H is nothing but, so let's say this is positive, and let this be origin. This point is origin. So if I have to draw, this is my positive direction, and this is origin. So the body was at origin and started moving towards the positive direction. So h will be taken as positive. So h is how much? I don't know. This is what is to be found out. What was u? U was clearly 0, because why was u 0? Because it was dropped freely. The other question could have been that it was pushed with a velocity of 5 meters per second or whatever. Okay, so hence yes, few of you have already calculated it. So hence it is, yeah, good. So hence basically now t is given as 4 seconds. So you will use what? Second equation. Second equation is s is equal to ut plus half. Yes, Ishani, correct. You have to use second equation, half gt square. Mind you, I have taken g as positive here. Why? Because my g is also towards my positive direction. So hence I have taken as positive. So and u was 0, so I know s, which is nothing but h. In this case, ut is 0t plus half into 10 into t square, so 4 square. So it is 80 meters. Another thing which you need to take care of is you guys take care of only the value, and you really do not care about the units. Please understand, in physics, if you miss out on units are the soul of the problem solving. So hence don't miss out, or don't make mistakes in converting one unit into another. Good. So answer is clearly 80 meters. Very good. So you guys could solve it. Let me take another question. Okay, all ready? Yeah, so 80 is the correct answer. Good guys, you are doing good. Next, let's take this question. Question says, question number 2. All set. Let's see who can solve it fastest. So question number 2 says a ball is thrown. A ball is thrown. A ball is thrown vertically upwards. Vertically upwards. Vertically upwards with an initial velocity. With an initial velocity equal to 49 meters per second. 49 meters per second. Okay, so you have to calculate. One, the maximum height attained. Maximum height attained. Two, the time taken by it before it reaches the ground again. The time taken by it before it reaches. G is taken, should be taken as 9.8 before it reaches the ground. G value is given as 9.8 meter per second square. See, guys, the moment you see numbers like 49, 198, 96, 98, 196, and things like that, you should be actually tempted to use 9.8 only. Yeah, so hence, be careful. Yeah, try and solve. I'll give you a couple of minutes to think over it. And meanwhile, I'll just, so hence, what's the protocol? Draw a representative diagram. So a ball is thrown vertically upwards. That means this is my surface. Always draw a representative diagram. So let's say this was the ball initially and it was thrown up. And after some time, it reaches the highest point. Okay. And then it starts coming down. And then after some point, it is back here. I am just drawing separately to just show. Otherwise, you know, it will come back exactly the same point where it is right now on the left side. Yeah. So this is how it is. So hence, what is happening? This guy is going up. Let's say this is the maximum height attained. And while coming down also, it will have the same height, same distance traveled. Okay, and the catch of this question is, the catch of the question is the time taken to go up, t to go up is same as t to come down. And the other information will be that at the highest point, what is the velocity? Velocity at highest point will be 0 because it will be instantaneously at rest. Okay, so this was u, and u was given as 49 meter per second. Okay, goes up, you have to find out what maximum height attained. Okay, so hence now you have to choose one, you know, one coordinate axis, one positive, negative direction. So what will I do? I will take this as my positive. Oh, let me choose it from, let me use another color. So I'm saying this will become my positive direction, and this is my origin, 0, origin, right? So this is positive. So what do I get? I get u as plus 49 meter per second. Why? Because u and this thing are in the same direction. Okay. Acha. H, while going up, let's say h unknown, I don't know. T unknown, I don't know. And while going up, final velocity is 0 because at the highest point it will stop and then only it will start coming back. So this is good enough for finding out. Acha, what is g for that matter? A is negative g minus 9.8 meter per second square. Why? Because my positive is upward and g is acting downwards, so it is negative. Very good. So let us apply what? Third equation will help me get the h directly. So third equation is v square equals to u square plus 2as. Right? So what is v? 0. So 0 equals u. What was u? 49 square. Yeah, it's in meter per second. Please be careful. Then plus 2. Then a is minus 9.8. Then s, this is what you have to find out. S is nothing but h. So hence I can write h equals 49 square upon 2 into 9.8. Yeah, 49 square into 2 into 9.8. If you do, what will happen? Let's simplify. This is 49 into 49. And this one is 2 into 98. And this is decimal, so I can write a 10 over here. This is how you simplify. So 49 goes, this is 2. Yeah, so this is nothing but how much? 490 by 4. Yeah, and this is nothing but 1 and then 2 and 2. What? And what is the unit? Meters. Yeah, so many of you have got the right answer. And the time taken. Time taken is very simple. So you can find out the time taken from the first equation. V is equal to u plus at. Deploy the values. V is 0. U was 49. And minus 9.8 into t. So t is clearly 5 seconds. It is for that going up. So for going down also 5 seconds. So total time taken to come down is 10 seconds, right? So time, this was for going up only. So time taken for a round trip. For a round trip is equal to 5 plus 5. 10 seconds. This is the answer. You can use Ishani. You can use second equation, but then you first for that you have to first calculate time t, and then use it. There is absolutely no problem in using any of the equation till you get the answer correctly. The only thing is, how do I get it faster? Yeah. So hence you have to be smart enough to why, because it's the exam is not only to get the answer correctly, but to also get answer correctly in lesser amount of time. Okay. So hence you have to be careful that okay, or you have to be cautious that okay, my efforts are reduced. So hence if you would have used the third equation in the one step itself, you will get the. Now how do we pick which equation to use? This is a common confusion with students. So what we do is we we say that okay, how many players are there? So in the second equation, if you see, second equation was s is equal to ut plus half at square, isn't it? Now here, if you use this, there are two unknowns. First, you don't know t, and second, you don't know s. So to calculate p first, you have to go back to the first equation and then deploy it here. Yeah. So which is in this case the effort is same. Why? Because there are two questions and hence. But let's say if there was no value in finding out this s, there was no marks allotted to that, then it becomes different. Here, you have to first find out time t and then deploy it here. Since the two questions are asked here, so it becomes same effort. But you should be careful enough to use that equation where you get the answer directly. So with multiple such questions practicing, you will get this. Okay, so never mind. So let's move on to but there is no restriction at whatsoever. So if you can do the same thing within and if you think that is easier for you to calculate, there is absolutely no restriction on choosing what particular formula or equation you are using. Now we will discuss about the final thing, and which is difference between mass and weight. So what is difference between mass? And most of you actually use it interchangeably, which is an incorrect thing to do. Right? So mass is nothing but, if you see, it's nothing but it's the measure of the quantity of matter contained. So what is it? First point is measure of matter contained measure of matter contained in the body. Okay, right? So this is the how much matter is there within a body is what is we measure through mass. Yeah, and later on in Newton's law, you also saw that we mass is also a measure of the inertia of a body. What was inertia? The tendency of a body to resist change was called inertia. So mass is related to these, right? Now weight is a force. So it is a force by which Earth pulls an object towards itself, object towards its center. Okay, this is the difference number one. So what did we learn? First of all, weight is a force. So hence its unit will be Newton, but mass is a quantum of matter in it. So hence we have a different unit for it, which is called kg. Second is clearly it's a scalar quantity. And weight also directed towards the center of the earth, so hence it is a vector quantity. Vector quantity. Okay. Now its SI unit is kilogram, and its SI unit is Newton. Newton. Not like that. Is N or Newton. Okay, then very important thing. It doesn't vary with time and space. Meaning, whether you measure the mass today or 10 days later or here or on moon, it will stay constant until unless it starts traveling with a very high speed where classical mechanics, realm ends and relativistic mechanics, the Einstein's theory starts. So we are not going there. So hence mass for all practical purposes remains constant. But this guy changes with position, changes with space. If it doesn't change with time, it definitely changes with why weight is a force? Because force is a vector quantity. And why is this force? Because this is the force with which the earth attracts any object towards its center. So hence, if you see, it is always directed towards the center of the earth. Hence, it is a vector quantity. In vector quantity, what did we learn? It doesn't only have a magnitude, but direction as well. So hence, since weight is a force, it's a vector quantity. Okay. Okay. Now, here is that it is measured by a beam balance. So if you have seen beam balance, there are two pans. Right? So, and then here it is measured by a spring balance, which takes care of, so spring balance, if you see, what's a spring balance? So there is a spring attached to it, and then there are graduations along it, and there is a spring which goes inside. Okay, so and then there is a hook here on which the mass is suspended. Okay, and it is fixed here. So higher the pull by the earth, and let's say there will be a indicator. There will be a indicator like that. So let's say this indicator is fixed with the spring. So if the earth pulls this thing down, the indicator will. So let's say this is 0 kg. This is, let's say, 10 kgs. So it is, let's say, 4 kg. So if it is 5 kg, then 4 will become 5. So in weighing scales used at home, does it measure weight or mass? Okay, very good question. It actually weight and mass are very closely related, right? So in the, let's say in the early morning when you stand up on that weighing balance, it actually measures your weight only. Why? Because there is something called a strain gauge which is inside, which works on the principle of expand, or let's say if you pressurize it, it expands. Now pressure obviously is force per area, if you remember. So hence, no. So please understand. Don't counter comment, guys. So what I'm trying to say is, when you are standing on the weighing balance, it takes your weight as the input, but always shows your mass. Why? Because if you see, weight is directly proportional to mass here. If G is constant, so W is mg, isn't it? So if you know G, and if you know W, you can find M. So your weighing balance, what does it do? It finds out your W, divides it by G, and throws you M. But it does take the weight into consideration. Now, there's absolutely no way to find out mass. There's absolutely no way to directly measure how much amount of matter is there. It's always indirectly found out. Either you take up, this equation where, the same thing, where if you see, this is Newton's second law, which is in use to find out mass. There is no direct way of finding out mass. So hence, you do what? You find out the force divided by its acceleration, you get the mass of the body. I hope that's clear to you guys. Okay, so this is the differentiator between now and I hope you have a clear understanding what is mass, what is weight, and weight is a force, mass is the absolute quantity. And yeah, so one other thing which I forgot to mention here when I was discussing this, the variation of G. If you see, G depends on what all values? Capital G, then the mass of the planet on which it is happening, and the radius of the planet, isn't it? So hence, if you go to moon, then instead of mass of Earth, you will have mass of moon over there. So Aryan is asking, sir, then what way our mass changes every other time period? What does that mean? No, our mass doesn't change, sorry, Aryan. Our mass doesn't change. Mass remains constant. Our mass remains always constant. Only weight changes. Okay, weight changes when you are either on the let's say on the Earth's surface, or let's say you go 200 kilometers above Earth's surface, your weight will change. And if you go in space, you will be weightless. That's what weightlessness is. If you remember, all these astronauts, they get a weightlessness training, zero gravity, where you will not be able to even stand on the floor of the space station. So you'll keep floating, right? So if you go beyond a point above Earth's surface, the Earth's gravitational fields become so weak that the G becomes zero, and you start floating. There is nothing which attracts you towards the Earth, and hence you start floating. And this also happens in free fall. So when you are freely falling, again, you experience weightlessness. Okay, yeah. Any other question related to that? So what I was trying to say is, as you go to different space or different places, your G will change. So usually, if you are weighing 6 kg here on, or 6 kg force, or let's say 60 Newton here on Earth, your weight will become 10 Newton on Moon. I got confused. W by what? The W is mg formula. Yes. So W is equals to mg. So if you know W and if you know G, you can find out M, isn't it, Aryan? Okay, fair enough. So I think we are done for the day, and I would expect you to solve your at least NCERT numerical problems, and the books which we have provided to you, it also contains a lot of numericals. And this is what is in in your gravitation chapter. We will try and schedule one more session where we'll try to revise the previous 2 topics as well. So I hope you guys enjoyed the session. If you really enjoyed it, I would request you to like it, and also subscribe to the channel so that you guys can be updated about the next videos. And if you have any question, you can put it in the comment section. Our team is going to scan through the comments and take out the questions from there, and they will try and respond back to you in as short time as possible. So you can post your queries either here on the group, wherever, and if you're posting it here, then the team who is following that comments will try to come up with a solution and post it back to you, so you can refer to that video. So in your leisure time, when you're free, go back and go through the video again, and whenever you require it, you can slow down the pace if you need and understand. And let's say if you didn't understand any particular point, you can highlight that in the comment, that at this particular time window I didn't understand, and we'll try to reach back to you as much as possible. So we'll end the session here, and we keep, and we'll be posting our next steps on the group as well as here on the YouTube homepage. Thanks a lot. So we will be signing off now, and let's meet again in the class and discuss it further. Thanks a lot, all of you.